Something happened today that briefly confused earthquake watchers around the world. The United States Geological Survey and the European Mediterranean Seismological Center published alerts within seconds of each other for what appeared on live maps to be two separate earthquakes, almost side by side in the middle of the Atlantic Ocean. For a few minutes, the question going around seismology forums was the same: is this a swarm? Is something bigger building? It was one event, magnitude 6.6, Central Mid-Atlantic Ridge, June the 17th, 2026, at 18 hours and 56 minutes UTC. Location, 0.525 degrees south, 20.015 degrees west. Depth, 10 kilometers, 6.2 miles, practically on the equator. The physics behind what happened today is something most earthquake coverage skips entirely. The Mid-Atlantic Ridge is the longest mountain range on Earth. 16,000 kilometers, 9,940 miles, of continuous underwater terrain running from north of Iceland to below the southern tip of Africa. It runs straight down the middle of the Atlantic like a seam. Most of it sits 2 to 3 kilometers, 1.2 to 1.9 miles, below sea level. If the Atlantic Ocean somehow drained overnight, what you would see would rearrange your mental picture of this planet. A continuous chain of peaks, volcanic ridges, and deep rift valleys bisecting the entire basin from pole to pole. Iceland is where it breaks the surface in the north. The Azores, Ascension Island, St. Helena, these are the ridge's high points showing above water. Today's earthquake happened in the equatorial section, which is the most seismically complex stretch of the entire structure. Sources for today's video are in the description. Everything we cover here is documented. The Mid-Atlantic Ridge is a divergent plate boundary, the place where the South American plate and the African plate are pulling away from each other. The rate is roughly 2 to 3 centimeters per year, about the speed your fingernails grow. This process has been running for approximately 140 million years. That's how the Atlantic Ocean was created. It started as a narrow seaway, something close to today's Red Sea, with what would become South America and Africa still joined at the hip. The ridge is the scar of their separation, and it is still widening right now, continuously. Including, while you watch this, subscribe if you want more of this, more earthquakes, more plate tectonics, more of what's actually happening under the ocean floor. At the equatorial section of the ridge, the geometry becomes complicated in ways that matter seismically. The ridge doesn't run as a single continuous straight line. It's offset repeatedly by transform faults, lateral fractures that cut perpendicular to the main rift axis. At these offsets, adjacent ridge segments aren't pulling apart. They're sliding horizontally past each other. The Romanche fracture zone sits just south of today's epicenter. It's one of the deepest and most seismically active transform structures on the planet, with a lateral displacement of around 900 kilometers, 560 miles, and ocean trenches reaching nearly 8 kilometers, 4.9 miles, below sea level. The chain fracture zone runs parallel a few hundred kilometers to the north. Between and around these structures, stress accumulates in a very different pattern than at the rift zones themselves. That is exactly why today's magnitude 6.6 happened here. A depth of 10 kilometers, 6.2 miles, at a divergent boundary tells a specific geological story. The lithosphere is thin at the ridge. The rock here is young, hot, and close to the mantle. There is no ancient, cold, oceanic slab descending hundreds of kilometers below. The zone where rock can store and release stress is relatively shallow. When an earthquake of this size occurs at 10 kilometers depth along a ridge transform, it is not an anomaly. It is the spreading center accommodating strain at a fault offset. The USGS Global Seismographic Network operates monitoring stations distributed across the Americas, Pacific territories, and international sites. The EMSC draws on European and Mediterranean arrays, with dense coverage across southern Europe, North Africa, and Atlantic island stations. When a significant earthquake occurs in the mid-Atlantic, both networks receive the seismic waves at nearly the same time, process them independently with their own algorithms, and publish separate solutions. The timing gap between publications is often under 60 seconds. On map platforms that aggregate multiple data feeds simultaneously, this creates exactly what people saw today. Two markers appearing within seconds of each other at almost identical coordinates, before cross-referencing consolidates them into a single confirmed event. Independent confirmation from two separate global networks arriving at the same magnitude and location. That's the system working. Both agencies said magnitude 6.6. Trust that number. 6.6 at a divergent boundary is a different animal than 6.6 at a subduction zone. The mechanics are different in ways that matter. At a subduction fault, the Cascadia system along the Pacific Northwest coast, or the Japan Trench, a 6.6 can represent partial release on a locked megathrust system that may eventually produce a magnitude 8 or 9. At the Mid-Atlantic Ridge, the physics is different. The plates are not being forced together and locked. They are being pulled apart, with magma rising continuously to fill the gap. Earthquakes here tend to be the rock's way of keeping up with the geometry of divergence, particularly at the transform offsets, where horizontal shear accumulates until it releases in events like today's. Since the Atlantic started opening 140 million years ago, the basin has grown from a narrow seaway to its current maximum width of roughly 8,000 kilometers, 4,970 miles at the equator. 2 to 3 centimeters per year, compounding across geological time. In the time it takes to watch this video, roughly 12 minutes, the South American and African plates will have moved approximately 0.01 millimeters further apart. That sounds like nothing, but run that rate for 100 million years and you get an ocean. Along the ridge itself, the geological activity goes well beyond seismicity. The rift zones where plates pull apart host some of the most extreme environments on Earth. Hydrothermal vent fields where superheated water, reaching up to 400 degrees Celsius, 752 degrees Fahrenheit, exits the ocean floor loaded with sulfides and minerals. These systems support entire ecosystems. Tube worms, chemosynthetic bacteria, shrimp species found nowhere else, that run on chemical energy rather than sunlight. Scientists first discovered these vent communities along the Galapagos Rift in 1977, and since then, dozens of active vent fields have been mapped along the mid-Atlantic ridge. Some of the richest are in the equatorial section, within a few hundred kilometers of today's epicenter. The seafloor spreading at the ridge also created one of the most important pieces of evidence for plate tectonic theory. As magma rises and cools at the rift axis, iron-bearing minerals in the new rock align with Earth's magnetic field at the time of cooling. Since Earth's magnetic field reverses periodically, the last major reversal was around 780,000 years ago, the ocean floor preserves a record of these reversals in symmetrical magnetic stripes running parallel to the ridge on both sides. When oceanographers mapped these patterns in the 1960s, the symmetry was unmistakable. The ocean floor was spreading outward from the ridge axis, and the magnetic record proved it. Today's earthquake happened on a structure that carries that geological archive in its rocks. Today's event had limited impact for one reason: location. No populated area sits within 2,000 kilometers, 1,240 miles of the epicenter. The nearest landmasses are Ascension Island, a British overseas territory with roughly 800 residents, about 1,200 kilometers, 745 miles, to the east, and the Brazilian coast, around 2,800 kilometers, 1,740 miles, to the west. No tsunami followed. Transform fault earthquakes move rock horizontally, not vertically. Tsunamis need the seafloor to heave upward. That didn't happen here. What makes today worth documenting is the combination of factors: the magnitude, the equatorial location, the near simultaneous dual agency detection, and the geological